This training is designed to prepare remote pilots for the weight, balance, and center of gravity portion of the Part 107 knowledge test, as well as helping ensure safe sUAS flights. The FAA expects sUAS remote pilots to understand how weight distribution, payload changes, and center of gravity location affect safe aircraft control. This training will focus on these areas. The first section will focus on center of gravity and its impacts on flight operations. First, you must understand what the center of gravity, or CG, means and why it matters. The drone's center of gravity is the precise point where its weight is balanced in all directions, typically centered within the frame, usually near the flight controller, for optimal stability, control, and efficiency. It matters because an incorrect center of gravity can cause flight instability, drone unpredictable behavior, excess power consumption, reduced control authority, and loss of altitude during maneuvers. The effects of an AFT or rearward center of gravity are less stable flight operations, more responsive controls, and higher risk of uncontrolled pitch up. Pitch up is the backward tilting movement of a drone's nose. The effects of a forward center of gravity are more stable flight operations, less responsive control of the drone, and requires more lift, which reduces flight endurance. The center of gravity is changed as the result of adding or removing a payload. The platform's center of gravity is designed based on the original configuration or package it came with. Altering it will affect the unit's center of gravity. Changing cameras, batteries, and sensors. Again, the design of the drone is based on the standard cameras, batteries, and sensors that came with the unit when it was purchased. Installing new components can have a negative effect on its center of gravity. And redistributing the onboard weight. Moving the weight of the payload or components can cause serious center of gravity issues. The center of gravity rule for Part 107 that must be remembered is that you must not fly if the center of gravity is outside the manufacturer's limits, the payload is not secured, and if the aircraft becomes unstable during flight. Next, we will focus on loading and securing payloads to sUASs. A drone pilot and crew must understand loads and why payload securement matters. A shifting payload changes the center of gravity mid-flight. Both forward and aft changes will negatively affect performance and flyability. Causes excessive pitch or roll corrections. Ultimately, the drone will be harder to control. Can lead to flyaway conditions. Flyaway is an uncontrolled incident where a drone stops responding to controller inputs and flies away on its own, and can cause auto-landing or loss of altitude. In other words, the drone may crash. How should payloads be attached? Correct attachments can include securely fastening the load to the drone. It may be beneficial to consult the manufacturer's user manual for recommendations. Ensuring the payload cannot shift in flight. Pre-flight inspections must be done to verify the payload is secure. Making sure the payload does not obstruct control surfaces, propellers, or sensors. Obstructions to key operational components will lead to issues during takeoff or while in flight, and must not create uncontrolled aerodynamic effects. This is especially important if there will be a lot of course adjustments during flight because the gravity effects will be impacted by the increased weight. The heavier the payload, the increased weight effects it will have on drone performance. Issues that can be dealt with include a slower climb rate, more power required to generate lift, shorter the flight time due to draining the battery quicker, and longer the stopping distance required when landing. The typical performance losses due to weight that will be realized are 5 to 20% reduced flight time due to a greater voltage pull on the battery. This should be obvious, as the higher weight increases the draw on the unit's battery. Slower acceleration. The sUAS propellers will strain to accelerate as weight is added to the platform. Reduce maneuverability. This is for the same reason as slower acceleration. And higher stall speed for fixed-wing systems, especially in turns and banking. A heavier aircraft in windy conditions effects can include better wind penetration, worse acceleration and braking, and more strain on the motor. Next, let's look at aerodynamics and load factor. Aerodynamics is the branch of fluid perspective studying how gases, particularly air, interact with moving solid objects, such as sUASs. Drone load factor is the ratio of lift supported by the propellers to the actual weight of the aircraft, directly affecting maneuvering and structural stress, especially in bank turns. It increases with bank angle, requiring more thrust to prevent altitude loss, which can lead to accelerated stalls. Load factor effects can be quantified in the following way. A level flight has a 1g effect on the platform. When a drone makes a 30-degree bank, it increases to 1.15 Gs. A 45-degree bank has a 1.41 G effect. And a 60-degree bank has a 2G impact, essentially doubling the weight on the drone. On the Part 107 exam, you will likely see a question like, if an sUAS weighs 50 pounds, what is the approximate weight the structure must support in a 30-degree bank turn? Additionally, you will be given a chart as seen to the right. To answer this question, take the weight of the sUAS, here 50 pounds, and multiply it by the load factor for the angle of bank from the chart. For 30 degrees it is 1.154. So, 50 times 1.154 is 57.7. Density altitude is an important factor to understand for drone pilots. Density altitude is the pressure altitude adjusted for non-standard temperature, representing the altitude in the standard atmosphere where air density equals the current air density. For sUAS operations, density altitude is how thin the air feels to the aircraft. High density altitude equals low air density, while low density altitude equates to high air density. Here is why this is important to know. The propeller blades work by pushing against the air to fly. So the thinner the air is, the less resistance the propellers are pushing against, therefore the drone must work harder to gain and maintain altitude. So you may wonder what causes high density altitude? Factors include high temperature, where the air molecules become lighter causing them to rise. High humidity. Water vapor found in humid conditions is lighter than air. So the more water in the atmosphere means there is less air, negatively affecting the thrust of sUAS propellers. And low pressure equates to lighter air, once again, making the propellers work harder to gain altitude. Here is an FAA exam trick that you should remember. High temperature equals high density altitude, which equals reduced performance. The effects of high-density altitude on drone flights include decreased thrust, reduced propeller efficiency, lower climb performance, higher power draw, shorter flight times, and overheating motors. Weather has great effects on drone performance. This will be the next subject covered. For success on the exam, and more importantly, success in safely operating a sUAS, a pilot must understand the effects weather has on performance. They include heat reduces battery lift and increases density altitude. Cold reduces battery efficiency and voltage stability. Humidity increases density altitude and reduces performance. Wind increases power consumption to maintain position. Rain adds weight and disrupts sensors. Many drone manufacturers operating manuals recommend not flying in the rain. And icing dangerously increases weight and significantly reduces lift capabilities. Hit the subscribe now to access the FSTG video on weather for a complete study guide on the Part 107 weather knowledge requirements. Next, let's look at battery performance. Drone battery performance is heavily influenced by capacity, weight, and environmental factors like wind or cold. Most batteries have an optimal performance occurring around 25 degrees Celsius or 77 degrees Fahrenheit. Battery efficiency decreases with cold weather, high power demands from climb, wind, and payload forces, rapid temperature changes, and old or improperly stored cells. As a drone owner, you must look for the signs of battery performance degradation. Some indicators include voltage sag, shortened flight times, inconsistent discharge curves, and overheating during charge. One way to ensure a drone is ready for load and performance challenges is by conducting pre-flight performance checks. A comprehensive sUAS pre-flight check ensures safety and legality by verifying the environment, aircraft, and controller. The FAA requires a pilot in command to inspect the following before flights: weight and balance. Verify that the weight is within the capabilities of the platform. Center of gravity position. Evaluate the loads in the unit to ensure proper center of gravity. Propellers and motors. Inspect the paddles and engine to make sure they are working properly. Battery health. Ensure the battery is charged, as well as connected and functioning correctly. Payload securement. If a payload is attached, inspect the connectors to verify it is secured to the platform. Airspace category. Verify there are no restrictions and the airspace allows for sUAS operations. And potential weather impacts on performance. Check weather reports to ensure there it is safe to fly. For airspace restrictions and weather checks, there are cell phone apps available, such as Before You Fly, Aloft, and UAV Forecast that can provide up-to-date information to make good decisions. Remote pilots, especially for commercial purposes, may find it beneficial to have inspection checklists developed and available to document pre-flight checks before taking off. This will not only benefit the pilot in ensuring the drone is ready for flight, but also provide documentation in case of an incident during flight. You can see an example of a pre-flight checklist here. You may be asked, when should you not fly based on performance? Considerations not to fly are when the aircraft is overloaded, the weight shift is expected, the manufacturer's limits are exceeded, the aircraft shows reduced responsiveness, and the batteries cannot sustain required power. And last, we will cover lost link and return to home behavior. A lost link occurs when the command or control uplink connection between the drone and controller fails. This can create a dangerous situation because the drone can fly into a structure and cause damage, or worse, into a person and lead to an injury. Most modern drones these days have a return to home, or RTH safety feature in case of a lost connection to its controller. Return to home is a critical, GPS-enabled safety feature in modern drones that automatically navigates the aircraft back to its takeoff point during signal loss, low battery, or user command. Some return to home or lost link considerations include: heavy aircraft slows climb. Low power batteries may fail during return. High density altitude reduces climb capability. And wind may overpower aircraft, preventing it from achieving its return to home objective. Understanding sUAS loading and performance considerations are important for safe drone operation and required knowledge for the Part 107 Knowledge Assessment. Thank you for watching this video. Please hit the subscribe button to access additional FSTG videos.